semiconductors and insulators. In this topic, the following subtopics will be discussed: conductors, semiconductors and insulators, intrinsic semiconductors and extrinsic semiconductors, p-n junction diodes, and application of diodes. Introduction. The knowledge of electronics is widely applied in the manufacture of electronic devices like TVs, radios, computers, mobile phones, among others. Semiconductors are major components in the circuits which aid in the operation of these devices. Conductors and insulators. Materials which have free electrons within their structure are called conductors. The animation below shows the structure of a good conductor and an insulator. Click on the word conductor and observe what happens. Repeat these with the insulator and observe what happens. Observation. When the conductor is used to complete the gap, electrons flow, causing current to flow. The bulb lights. When the insulator is used to complete the gap, the bulb does not light. Explanation. All materials contain two bands where electrons are found. These are the valence band and the conduction band. The two are separated by a gap known as the forbidden gap. There are no electrons in the forbidden gap. Insulators. In insulators, the forbidden gap is too wide such that the electrons require a lot of energy to be exited into the conduction band. Click on the play button of the animation below to see visualization on this. Conductors. In conductors, the valence and conduction bands overlap. The forbidden band doesn't exist. Electrons are free and mobile to conduct current. Play the animation below to observe the behavior of electrons in a conductor. Semiconductor. In these materials, the forbidden gap is not as wide as in insulators. At low temperatures, all the electrons are in the valence band. However, at room temperature, some electrons gain thermal energy and overcome the forbidden gap. The materials then become a conductor. Examples are silicon and germanium. Click on the play button of the animation below to see how electrons behave in semiconductors. Types of semiconductors. There are two types of semiconductors: intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors. Silicon has an atomic number of 14. Its electronic configuration is 284. The diagram below shows a silicon lattice structure. Explanation. At low temperatures, all the electrons are held up in the covalent bonds. At high temperatures, some electrons gain heat energy. The bond is broken and they move to the conduction band. The free electrons move freely within the lattice and are available for conduction. A free electron leaves a positive space referred to as a hole. This creates instability by attracting electrons from the neighboring atoms, causing a net movement of electrons. Play the animation below to observe this. When the material is connected to a circuit, the electrons flow in one direction, making the hole to drift in the opposite direction. Conduction in intrinsic semiconductors. The animation below shows how electrons in an intrinsic semiconductors behave when in an electric circuit. Click on its play button and make your observations. Extrinsic semiconductors. These are materials whose conductivity is increased by adding small amounts of impurities into the pure material. The process is called doping. The materials which are doped are known as extrinsic semiconductors. There are two types of extrinsic semiconductors: p-type semiconductors and n-type semiconductors. P-type semiconductors. This is obtained by doping the material with a group 3 element like aluminium, boron, and gallium. The animation below shows how the semiconductor is doped. Click on the Dope button and observe what happens. N-type semiconductor. This is obtained by doping a semiconductor with a group 5 element like phosphorus, antimony, arsenic, among others. The animation below shows how the semiconductor is doped. Click on the Dope button and observe what happens. The junction diode. A p-type semiconductor can be joined to an n-type semiconductor of the same material to form a p-n junction diode. Once the junction is formed, the holes in the p-type near the junction moves towards the n-type side, and the electrons in the n-type near the junction cross over towards the p-type side. The movement causes neutralization around the junction. This creates a barrier there which prevents further movement of charges. This barrier is called the depletion layer. The animation below shows how a depletion layer is formed. Click on the play button to observe how this takes place. Click on the play button to make your observations. Forward bias. This is connecting a p-n junction diode to a PD in such a way that the p-type is connected to the positive terminal and the n-type to the negative terminal. The animation below shows the forward bias connection. Observation. The negative charges move towards the p-type side and the positive charges towards the n-type side. Current flows and the bulb lights. Explanation. The positive terminal of the cell repels the holes towards the n-type side and attracts the electrons. The negative terminal of the cell repels the electrons from the n side and attracts the holes. This reduces the size of the depletion layer, making it easy for charges to cross over and current flows. Forward bias characteristic. The sketch below is an illustration showing the IV relationship. Reverse biasing. This is connecting a p-n junction to a PD in such a way that the p-type is connected to the negative terminal and the n-type to the negative terminal. The animation below shows reverse bias connection. Play it and make your observations. Application of diodes. Rectification. This is transformation of an alternating current into a direct current. A diode is used in rectification because of its property of exhibiting high resistance when reverse biased and low resistance when forward biased. There are two ways of rectifying an alternating current: half-wave rectification and full-wave rectification. An AC connected to a CRO displays a graph as shown. This gives the form of the wave to be rectified. Click Next to view a visualization on this. Click on the play button to make your observations. half-wave rectification. In half-wave rectification, a diode is connected to the circuit. In the first half cycle of the AC, the diode becomes forward biased and allows the current to flow through. In the reverse cycle, the diode becomes reverse biased and cuts off the current flow and the second part of the curve on the CRO. The animation below shows how a half-wave rectification is done. Click on the play button and observe what happens. Observation. Current in the first half cycle is seen to flow, but the second half cycle is cut off. A half wave is displayed on the CRO. Full wave rectification. There are two ways of achieving this connection, either by using two diodes with a center-tapped transformer or using four diodes. Using two diodes. The animation below shows how an AC can be rectified using two diodes. Play it and make your observations. Observation. When the switch is closed, half waves are displayed on the screen. Explanation. In the first half cycle, current flows through C, A, D1, RL, and back to C. A half wave is displayed on the CRO. In the second half cycle, current flows through C, D2, B, RL, and back to C. The second half wave is displayed on the CRO. The process continues and many half waves are displayed. Using four diodes. The animation below shows how four diodes can be used in full wave rectification. Click on the play button to observe how this is done. Observation. When the switch is closed, half waves are displayed on the screen of the CRO. Explanation. When the switch is closed in the first half cycle, current moves from source to D4, RL, D3, and back. A half cycle is seen in the CRO. In the second half cycle, current moves to D2, RL, D3, and back to the source. Another half cycle is displayed on the screen. The process is repeated and a series of half waves is seen on the CRO.